All right, this video is over the central limit theorem. As the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with a mean of mu and a standard deviation of sigma will approach a normal distribution. This distribution will have a mean mu and a standard deviation of sigma divided by the square root of n. So what does that mean? Well, let's take an example. Let's say x represents an individual test score. So we have a whole bunch of people take some test, and each x might represent a test score. And we fill up the distribution, and if I fill up all this area with x's, this shape kind of represents the test scores. So we've got a few people that did poor, a bunch of people right in this range, not very many people in the middle. We've got a lot of people that scored right in here, and maybe one or two that scored really high up here. So it's not normally distributed when we look at the individual scores. Then let's say that we now decide, instead of looking at individual scores, we're going to pick 3 students and find their average score. And whatever their average is, that's what x is going to represent. Instead of x, maybe we should use dots here. Dot representing a test score. Maybe that's the average of 3 students' test scores. Then we pick a different 3. Well, it could actually be this. It could be like 2 out of the 3 could be the same person because it says with replacement. So we're putting the students back into the class. We pick 3 again, not the same 3, but 2 out of the 3 could be the same. And again, each dot now is not going to represent 1 test score, but the average of 3 test scores. So this horizontal axis now represents x bar instead of x. If we do that, what we'll find is the data won't be as spread out, because these people who scored really high will probably be averaged with somebody that scored lower. These people that scored lower will be averaged with somebody that scored higher. So our data will actually be squeezed in. So our data might look something like this. And it may not be totally normally distributed. But we should, I want to make sure I emphasize that the data will be squeezed in. Now what will it be squeezed in towards? It'll be squeezed in towards the mean. Let's say, for example, that the mean up here is approximately right here. That's the mean. The mean of this sample, let's say, is right here. Now the mean of the sample means will look like that. Okay? This is a mean of the x values. This is a mean of the sample means. So in other words, we would take all groups of 3 students and find their average test score, mark those on the graph, then take the average of those sample means. Now, one thing you'll find out is that the mean and the mean of the sample means are going to be equal if we looked at all possible combinations of 3 students. So what we're going to find out here is that the mean of the individual test scores will equal the mean of the sample test scores if we look at all possible groups of 3 students. If we go up to n equal 10, so now we pick 10 students and we find their average test score. Then we pick 10 again, and 10 again, and 10 again. What's going to happen is that data is going to get even squeezed in closer to the mean. So if our mean is about right here, the data is going to squeeze in even closer around that mean. The central limit theorem is what tells us that. It also tells us that the distribution will approach a normally shaped distribution. So we can see as our sample size gets larger, the data will get squeezed in towards the mean, and the data will become more normally distributed, more bell-shaped. Okay? So if our data is less spread out, the measurement that we use normally to determine how spread out data is the standard deviation, which looks like that. So if the data is getting less spread out, that standard deviation is getting smaller. Now, the standard deviation of these 2 distributions would look like this. It's the standard deviation of the sample means. And actually, instead of calling it the standard deviation of the sample means, We normally change the wording, we call it the standard error of the means. And the way we find that standard error is we take our standard deviation divided by the square root of n. Same thing down here, we would take the standard deviation divided by the square root of n. If you think about it, as n gets larger, the denominator here would get larger, so we'd be dividing by a larger and larger number, which is going to make this answer, this total answer, get smaller. So as n gets larger, the standard deviation, or standard error of the means, gets smaller, which means the data gets scrunched in towards the mean. See if I'm forgetting anything here. As the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. You can see it becomes more normal as we go down, as n gets larger. The distribution will have a mean of mu and a standard deviation divided by the square root of n. And again, we call that the standard error of the means. The other thing that comes into play here is your z-score. The general formula for a z-score is to take your data value minus the mean divided by the standard deviation. And here's the formula we generally use. So as long as we're dealing with individual data points, x values, that is the correct formula. But if the standard deviation is no longer just simply that symbol, now it's standard deviation divided by the square root of n, and we need to divide by that in a denominator here. So when you see a problem where they're talking about the mean of a group of tests, or the mean height of a group of people, or the mean, if they're using sample means in the problem, then we want to use this z-score formula instead of this z-score formula. And the other thing that we'll do a lot of times is, since the mean equals the mean of the sample means, a lot of times we'll just call these mu, because they're equal. And that's the central limit theorem from section 6.5.